So today we are covering chapter 12 exercises. And as usual, I already scrolled to the answers. All of the questions are repeated in full before the answer. So first couple of pages are actual questions and then they are not shown here. We are starting on page 3 where we have question 1. So all the questions are repeated in full followed by an answer. So which of the following is the strongest nucleophile? And then you have 4 choices. This is actually something we covered in chapter 6, and now we are doing it again because now it's application of that material. Nucleophile is species that is capable of donating electron pair. So by definition, nucleophile must have free electron pair. Strong nucleophile has high tendency to donate free electron pair, and weak nucleophile obviously have weak tendency. So which one will have stronger tendency? Well, those atoms that are larger will have that free electron pair further away from the nucleus, and then that electron pair will be experiencing less of the attraction with the positively charged nucleus, so it's going to be stronger nucleophile compared to smaller atom. And of course, as you know, size of an atom increases going down the group of periodic table. That means that those lower in the group will be stronger nucleophiles compared to those higher. So, for example, sulfur is stronger nucleophile than oxygen, and selenium stronger than sulfur, and so on. Phosphorus stronger than nitrogen, or among halogens. Bromine stronger nucleophile than chlorine. Iodine stronger than bromine. Nucleophilicity is also related to electronegativity. Electronegative atoms actually tend to hang on to their electron pairs quite strongly. So less electronegative atom is stronger nucleophile. And electronegativity increases across a period of periodic table. So those to the left of the period, like nitrogen, will be stronger nucleophile than oxygen, and those to the right. And oxygen stronger than fluorine. Then third factor would be charge. Species that is charged is stronger nucleophile than one that is not, that has negative charge. Because obviously presence of charge is unstable, and so charges would tend to cancel out, or negative charge would tend to combine with positive charge, is attracted by positive charge. So such nucleophile with negative charge would seek electrophile to donate electropair to. But when it comes to charges, although general rule is that negatively charged species is stronger nucleophile, there are some exceptions. For example, fluoride anion, fluoride minus, is actually a weak nucleophile. But that's, I think, the only exception that you may know of. In general, when it comes to charges, we are comparing, for example, negatively charged oxygen is a stronger nucleophile compared to neutral oxygen, or negatively charged nitrogen, stronger nucleophile than neutral nitrogen, so on. And in general, that's how we compare them. We don't compare charged and uncharged species. Although you can draw conclusions, sometimes if you have to list them in the order, there are usually enough clues to be able to list them in the order. And then final fourth factor that you should know is steric hindrance. So even if something would be otherwise strong nucleophile, if there is presence of bulky groups next to the nucleophilic center, next to the atom that donates free electron pair, then it's going to be weak nucleophile, or maybe not a nucleophile at all, because steric hindrance prevents donation of that free electron pair. There are actually more than these 4 factors, but that's all that you need to know, just those 4. So size of the atom as related to its position within a group, electronegativity, so that's within a period, charge, and if present, steric hindrance. So let's consider here. First is ethanol. So there is no charge. It's oxygen nucleophile. It's moderate to weak nucleophile because there is no charge. Fluoride anion, there is charge, but it's actually not very strong because, as I said, fluoride is an exception. Because while it does carry negative charge, which would increase strength of a nucleophile, problem is that it's both small in size and highly electronegative. And so it's relatively weak. Iodine, that's actually strong nucleophile. It's a very large atom. Electronegativity is relatively low as far as, let's say, halogens go, and it has negative charge. Large negative charge, electronegativity, let's say, modest. So that's very strong nucleophile. And in fact, of the four, it's the strongest because the last one, dimethylamine, actually is neutral, has no charge. So it is actually reasonably good nucleophile, but we would say, let's say, moderately strong because it doesn't have charge. So C is correct answer. Next question. The following reaction gives a single product. Provide its complete UPAC name and make sure that you provide complete name for full credit. So emphasis is on complete name. And so you see, we have a reaction here. If you covered chapter 12 and you should have substitution reactions, this is a substitution reaction where leaving group, chloride anion, is being replaced by hydroxide. And it's indicated, stereochemistry is indicated, so it's a single enantiomer. And that's what complete name means. That's why there is emphasis on complete name. Since single enantiomer is starting material, you need to provide name of the product including stereochemistry. And so first you should recognize that this is SN2 reaction. This nucleophilic substitution could be unimolecular or bimolecular. Unimolecular SN1, bimolecular SN2. Strong nucleophile, this is secondary substrate. By the way, you should recognize substrates. If substrate is primary, then reaction is SN2. If it's tertiary, it's SN1. And then if it's secondary, then you look at the nucleophile, the reagent. So if it's primary or tertiary, you look at the substrate, starting material, alkyl halide. But if it's secondary alkyl halide, then you look at the reagent. Is it strong or weak nucleophile? And that's in part why you need to be able to recognize strong and weak nucleophiles. If it's weak, then reaction mechanism is SN1. If it's strong, it's SN2. This is strong nucleophile, hydroxide anion, negatively charged oxygen. Strong nucleophile, SN2, that means reaction proceeds with inversion of configuration. So if leaving group was projecting towards us, then when hydroxide replaces it, it's going to be projecting away from us. And so first you need to name this alcohol. So 4 carbons. Actually, this is not. Okay. It's actually butanol, not pentanol. I'll fix this right now. 4 carbons. That's butane. So alcohol is butanol. And a hydroxyl group is on the second carbon. So that's 2-butanol. On carbon, so this is 1, 2. On carbon 3, there is methyl group. So it's 3-methyl, 2-butanol. And then you need to indicate stereochemistry, whether it's R or S. In this case, a lowest priority substituent, hydrogen, is not shown. You should have pen and paper on the test, so you may want to include hydrogen, and then you will see if OH projects away from you and hydrogen is not shown, it must be projecting towards you. So to determine RS configuration, lowest priority substituent has to project away from you. So to send it back, you flip positions of OH and H, so that way hydrogen is at the back. But to keep an enantiomer the same, you also have to flip positions of the other 2 substituents, isopropyl group and methyl group. So at the same time, you flip all those. That really amounts to rotating it in space. Alternatively, you can make a model and then determine from a model whether it's R or S. And now from the model, you can assign priorities, or from this formula, oxygen priority 1, 2 carbons same priority, but then when on each of these 2 substituents, isopropyl and methyl, you follow path of highest priority. So it was carbon versus carbon tie, and then carbon versus hydrogen, not shown, high priority. So it's 1, 2, 3, or R. And again, let me fix this. This is butanol. So it's R, 3-methyl 2-butanol. So for full credit, you have to include RS. If you forget this RS, at best you can get partial credit. And then question number 3 is also related to it, and after I finish 3, then I will check if there are any questions. So which of the following nucleophiles favors SN1 reaction mechanism rather than SN2? And so that simply means which one is weak nucleophile. Because when it comes to nucleophiles, weak nucleophile favors SN1, strong SN2. So the question is which one is weak? A appears to be weak because there is no charge. It is oxygen nucleophile, so it does have some strength. It is a nucleophile, but no charge, we would consider it to be weak. A negatively charged sulfur, that's actually rather strong nucleophile. Negatively charged oxygen, we already figured out that's strong nucleophile. Some students would make a mistake and select D, because this is tertiary butanol. And this one actually has also oxygen, just like ethanol, but it has this bulky group. And since steric hindrance reduces strength of a nucleophile, students reason, well, this one, both have oxygen. Both are relatively weak, oxygen without charge, but D has steric hindrance, A does not, so D is weaker. But actually, D is not nucleophile at all. So that's the issue. Steric hindrance, when you consider steric hindrance, frequently steric hindrance doesn't just make nucleophile weak, it actually renders species not nucleophilic at all. And so tertiary butanol as alcohol is used not when we want weak nucleophile, but when we want some proton donor or proton acceptor, because alcohols are both proton donors and acceptors. If you want proton donor or acceptor that is not nucleophilic at all, that's when we use it in reaction. And so D is not correct answer, not because it's not a weak nucleophile, but because it's not nucleophile at all. And so be careful about that. At this time, I think about hindered nucleophiles. Tertiary butanol is the only one that you know. But basically anything that has tertiary carbon attached to OH or NH2, that would be hindered and it would not be nucleophilic. For nitrogen nucleophile, I don't teach organic 2, but we cover diisopropyl amine and diisopropyl amide. It's an ion. And those are also non-nucleophilic. Again, because of the presence of 2 diisopropyl groups on nitrogen. But that's second semester chemistry. So at this point, pretty much all that you're looking for is tertiary carbon, tertiary alcohol. If you have tertiary alcohol, then that's actually not a nucleophile. So you cannot say it's a weak nucleophile, because to be a weak nucleophile, it has to be nucleophile in the first place. And the tertiary alcohol is not a nucleophile at all. And something is misspelled here. And also here. Let me see if there are any more misspellings. Okay, that looks good. Okay. So, well, somebody asked, actually, what is the difference between strong and the weak nucleophiles? There is quite a bit in the textbook about that, so let me refer you to appropriate page. Because that's kind of open-ended question, there are lots of aspects to it. I can't really lecture like that right now. So it's page 296. So page 296 in the textbook, chapter 12, and then also chapter 6. Pages, let's see, yeah, 134, 135. So, yeah, otherwise, see, yeah. So that's how you would recognize one or the other. And also, like question, what is the difference? It also could mean functional difference. Let's say strong nucleophile favors SN2, weak SN1. Is primary nucleophile a stronger nucleophile than secondary? I'm not sure the difference is significant. So usually that would not be something that we would ask. Okay, any other questions? And there could be some instances, but it's difficult to say. Probably methanol, ethanol are stronger than the rest of the alcohols, but if we are talking about one pentanol versus two pentanol, I'm not sure there is significant difference. Okay, so let's go back to exercises. So question number 4. Tertiary alkyl halides cannot undergo SN2 reaction because. So why tertiary alkyl halides undergo only SN1 reactions? A, they are hindered. And that's actually correct answer, because SN2 reaction is highly sensitive to steric hindrance. Because in an SN2 reaction, it's bimolecular reaction, nucleophile displaces the leaving group. So nucleophile donates free electron pair in a backside attack. So let's see. So it has to be a backside attack where we have not that is correct actually. This one is correct one. So while carbon atom is originally tetrahedral, leaving group, like green atom in this case, is displaced by backside attack on the nucleophile. So in transition state, carbon atom is actually sp2 hybridized, and these two bonds are partially formed. Carbon leaving group and carbon nucleophile are partially formed. And so any steric hindrance is going to prevent attack of the nucleophile, any steric hindrance. So if you have something large, I just have some fragments here that may not be related to this course, but if you have some large substituent, see something large like this, that's going to prevent, and actually there will be hydrogen atoms here, which I didn't show, but it's going to prevent, I just put one hydrogen here. It's already going to show you hindrance. Let's put a couple of hydrogen atoms. And you see this, so this is the leaving group. And if this is nucleophile, which is some oxygen nucleophile, and that oxygen would have something on it, probably like methyl or ethyl group. Let's put few atoms on that oxygen. So like that. So it's negatively charged. So this oxygen actually cannot approach. You see that it's going to bump and cannot get to donate electron pair. By the way, you cannot consider it, well, what if these substituents were all down? Because of the thermal motion, all of these substituents constantly rotate in all directions in space, and so they are sweeping the space. And so when considering steric hindrance, you're assuming the worst case because there is this constant rotation. And so as oxygen is approaching reactive center, there's constantly going to be rotation here. And so it's going to rotate and approach. So it cannot, as you can see, it cannot approach. So steric hindrance prevents reaction. And so that's why tertiary substrates don't react. Primary carbocations are too unstable. That is true that primary carbocations are unstable, but they have been observed as intermediates in some other reactions. So while that is one of the reasons, it's not really the clinching reason. It's really primary carbocation. That's actually for why primary substrates don't undergo SN1 reactions. They flip to another question. So let's stick to tertiary alkyl halides cannot undergo SN2 reactions. So I just explained. So tertiary because of the steric hindrance. So tertiary alkyl halides don't give tertiary carbocations as intermediates, so this doesn't make sense. So halide ion is poor leaving group. That's not correct. Chlorine, bromine, and iodine are excellent leaving groups. Only fluorine is poor leaving group, but in general we understand when we talk about halogen atom as leaving group, we understand that fluorine is a special case and that we are ignoring it. Reaction is endothermic. Actually, it's not. It's exothermic. So correct answer is A. Steric hindrance. Question number 5. Which of the following undergoes SN2 reactions at the fastest rate? So different SN2 reactions. And you have 4 compounds. So we just discussed that SN2 reactions are sensitive to steric hindrance. So the least hindered compound will undergo SN2 reaction at the fastest rate. That means primary preferentially to secondary, and tertiary will not even undergo SN2 reaction at all. And then if you have several primary or several secondary that are tied, that are the most reactive, then you look which one is the least hindered. And so to figure that out, really the best is to draw a formula. So 3-chloro-3-methylpentane. So you just use pen and paper and draw it. And you can see that's tertiary. So that one doesn't undergo SN2 reactions at all. 2-chloropentane, that's secondary. That's all right. C, 1-chloropentane, primary. Primary versus secondary, primary is better. And D, 3-chloropentane, another secondary. This one is even more hindered than B. Well, actually, it's arguable, but 2-ethyl group versus methyl and propyl. So whether it's 1-propyl that is more, I would argue that D is more hindered, but it doesn't matter since you're not ranking them. You're looking only which one undergoes reaction at the fastest rate. And that's C, because C is the only primary substrate here. And then question number 6. Which of the following reactions proceeds at the fastest rate? First, you should recognize that these are SN1 reactions because while we have different substrates, we have actually bromide, but different bromides as substrates, nucleophile is always the same, water. Water is weak nucleophile. Weak nucleophile favors SN1 reaction. So this is SN1 reaction. So question is, which of the following SN1 reactions proceeds at the fastest rate? And then when you look at them, now reaction rate in SN1 reaction depends on the stability of the intermediate carbocation. And you may recall from chapter 9, tertiary carbocations are the most stable, then primary, tertiary, then secondary, then primary, and then methyl, least stable. So if there is any tertiary compound, it will react at fastest, at higher rate than any secondary higher than primary, and so on. So you consider these compounds. First one is tertiary, so that's actually pretty fast rate. B, that one is actually primary. That one actually would favor SN2 mechanism rather than SN1 because it's primary, and primary carbocations are unstable. So that's actually what I mentioned earlier when I got a little bit ahead with previous question and started discussing that point about primary carbocations being unstable. Actually, so B is unlikely to undergo SN1 reaction at all. So this reaction is unlikely to work at all. We would need really hydroxide here, like sodium hydroxide, for this reaction to proceed, not water. To favor SN2 reaction, because this is primary, and primary carbocations are generally not stable enough for this reaction to proceed at reasonable rate. C is also primary, same as B. And then D, that's secondary. This one would undergo SN1 reaction, just like A, but because it's secondary, at much slower rate. So really, A is the one that proceeds SN1 reactions, undergoes SN1 reaction or proceeds through SN1 reaction at the fastest rate. So correct answer is A. Okay, I'm going to stop recording here so that recording is of reasonable size, and then record Second part as separate video.